is liquid, and some materials are called solid solution in material science, like and called homogenization procedure. The topic of my presentation is mass transformation and reversibility mechanism in copper-based sheet-memory alloys. First of all, I intend to introduce the basic concept in materials science and shape-memory phenomena. Then I introduce the application of shape-memory effect to ternary copper-based shape-memory alloys. Shape-memory alloys have a peculiar property to return to a previously defined shape or dimension when they are subjected to variation of temperature. This behavior is related by the structural change caused by internal stresses in microscopic scale, and shape-memory effect is based on multi-state transformation. Shape-memory materials can be plastic deformed in low temperature multi-state condition and recover the original shape just by thermal means on heating over the reverse transition temperature after removing the state. Also, there's material cycle between the deformed and original shapes on cooling and heating. There are two kinds of shape-memory effects. One is irreversible one way, and the other is reversible shape-memory effect. The mechanism of shape-memory effects based on deformation of the material at the low temperature multi-state condition. If we can select an open coil materials, on cooling, the austerity phase turn into the multi-state phase in crystallographic level. And with the deformation, or plastic deformation, it deforms in multi-state condition, and on heating to recover the original shape of the material. Second, after cycle in one-way and two-way shape-memory effect, in the one-way shape-memory effect, the material doesn't recover the deformed shape on cooling. And in the reversible shape-memory effect, the material return to the deformed shape on cooling before under the critical temperatures, and on heating, the material recover the original shape and cycle between the deformed and original shapes on cooling and heating. Shape-memory behavior of shape-memory materials is evaluated by the microstructural change in atomic scale or Armstrong level caused by the internal stresses, whereas shape change occurs in macro or bulk level. Multi-state transformation occurs in materials in thermal manner on cooling from high temperature current phase, and it is characterized by changes in the crystal structure of material. Multi-state transformations are lattice distorting fast transformation and occur as thinning multi-site with cooperative movements of atoms over very short distance on the order of Armstrong by means of shape-like mechanisms. Thus, twin martensites occurring on cooling turn into determined martensites or reoriented martensites applying external stresses in the low temperature condition. Thus, processes are schematically illustrated as following. This is high temperature current phase structures. On cooling, the ordered structures turn into the determined martensites, and with the deformation, determined martensites turn into the determined or oriented martensite. And first heating, the determined stressed martensite turn into the current phase. And on cooling, the ordered current phase structures turn into the twin martensites in irreversible shape-memory effect, and ordered current phase structures turn into the determined martensite on cooling below the martensitic transformation temperature. Martensitic transformation is a first-order solid-state fast transition and occurs in a few steps with the cooperative movement of atoms in displacing manner. Therefore, these transitions have diffusionist characters, and product martensitic phase inherits the order of current austenitic phase. Martensitic transformation mainly occurs in two basic steps in beta phase region of materials which exhibit shape-memory effect. The first one is binding distortion, and the second one is lattice invariant shell. Basic beta phase structures. This basic body-centered cubic structures. This is the cesium chloride type unit cell. This is also dual-three type unit cell. The other is L21 type unit cell. Base distortion is a homogeneous distortion which consists of an expansion of 26% parallel to the 001 type axis and a compression of 11% parallel to the 110 and 1-1 type direction. An FCT cell is delineated as a first step in matrix beta phase structures, DO3 type structures, and this cell undergoes to the corresponding FCC lattice structures. Therefore, the selected FCT unit cell turns into an FCC unit cell with base distortion. Basic current phase structures and selection of an FCT unit cell, and with base distortions, FCT unit cells turn into the FCC phase-centered cubic unit cell. Lattice invariant shells or inhomogeneous shells occurs as martensite variants on a 1-1 type planes of austenite matrix, which is basal plane of fourth martensite. The lattice invariant shells occurs in two opposite directions, like 1-1 type direction on the 1-1 type planes, sharing in the 1-1 or -1 direction occurs as a variant along 1-1 type plane. Thus, shells cause to the formation of naive structures in the 1-1 type planes of current phase. into unusually layered structures which consist of an array of close pocket planes with complicated stacking sequence called as 3R, 9R, or 18R martensite, depending on the stacking sequences on the close pocket planes of the ordered lattice. The periodicity and therefore the unit cell is completed through 18R layers in direction Z in 18R layered structure case. The formation of layered structures is schematically illustrated in this figure. In the layers of planes 114 type beta phase in current phase structures, and this plane turn into the layer structures with the cooperative movement of the atom by means of shell-like deformation. This is also another illustration. In the present configuration, two copper-based ternary alloys selected compositions are also indicated in this scheme, and the critical transformation temperatures are over the room temperatures, and both of alloys are in the current phase martensitic condition in the room temperature. Specimens obtained from these alloys were solution treated for homogenization in the beta phase field as following, and then quenched in ice brine and aged at room temperature. Heating temperature, copper, zinc, aluminium, and copper aluminium alloys are 830 for copper zinc and 700 degrees for copper aluminium alloy. Further specimens for X-ray examination were prepared by filling the alloys. Further specimens were sealed in evacuated quartz tubes and given beta-phase homogenization treatments. This homogenization is heating at 830 degrees for 15 minutes for copper zinc aluminium alloys, and for copper aluminium alloys heated at 700 degrees for 15 minutes and quenched in ice grade. Further, diffractorams were obtained for all specimens at different stages of aging in a long-term interval. This is an X-ray diffractoram of copper, zinc, aluminium alloy sample. It exhibits that this sample has the ordered structures in the martensitic condition, and these peaks have great importance in the examination of the martensitic transformation. In particular, these phase have great importance. This is also X-ray diffractoram of copper aluminium alloys taken after aging at room temperatures about 10 years. The series of X-ray diffractorams have been taken from most of the alloy samples in a time interval, and some chunks have been observed in peak location and characteristics with aging duration. In particular, some of the successive peak pairs have shifted toward each other. As successive peak pairs provide the following relations. If N is for 18 arc martensites, as plate can be listed as follows for 18 arc structures, as seen from the X-ray diffractor. This space. That's phase 1 to 202, 1 to 8, 208, 1 to 10, 1 to 10, 210, 4, 4, 3 to 4. At the long-term investigation, nearly 10 years, it is observed that these peak pairs come close each other with aging duration. These chunks reveal the chunks in the crystal structure of material. Recently, the rearrangement of atoms in disordering manner in martensite conditions. The basal plane of martensite, which is 1,1,4 type plane, is subjected to the hexagonal distortion with martensite formation, on which atom size have important effect. In case the atoms occupying the lattice size have the same size, the basal plane of martensite becomes regular hexagon. Otherwise, the deviations occur from the hexagonal arrangement of atoms in case atom size are different. In the disordered case, all of the lattice size are occupied randomly. Atomic size can be taken approximately equal to each other. In the ordered case, lattice size are occupied regularly by certain atoms which have different atomic size, and basal plane deviates from the regular hexagonal arrangement of the atoms due to the atom size differences. As you can see, the basal plane turn into the hexagonal structures with martensite transformation. In the disordered case, atom sizes can be taken equal each other, and in this case, the hexagonal structure is ideal, regular, hexagonal. In the ordered case, the atom sizes occupying the lattice size are different, and in this case, the hexagon deviates from the ideal hexagon. Electron diffraction patterns also exhibit the superlattice reflections. microscopic scale by means of mathematical transformation. The fundamental structure of beta-type martensite are orthorhombic closed packet structures, which consist of parallel closed packet planes. The beta-type martensites have the layered structures and are characterized by the stacking sequences depending on the order in the parentheses. Copper-based ternary alloys have the dioptric superlattice in parent austentic case, and the following stacking sequence occurs with martensitic transformation: A, B, C, C, B, C, A, C, A, B, A, B, C, B, C, A, C, A, B, like that. On the basis of constant partistic relation, the buzzer plane of 9R or 18R martensite originates from one of the one-bona-type planes of the parent on which an homogeneous shield occurs in two opposite directions during the martensitic transformation. The basal plane of martensite is subjected to the hexagonal distortion formation on which atom size have important weight. In case of the ordered case, atom sizes can be taken approximately for each other. Therefore, this change in the disordering in martensite and can be a measure of the ordering degree in martensite. On the other hand, martensite structures undergo the disordering reaction in contrast to the ordered reaction in the pre-martensitic stage with the aging treatment in martensitic condition. Disordering reaction occurs as disorder transition and change between the related atoms take place with aging. Although martensitic transformations are diffusionless, the transition occurring during the aging in the martensitic condition have a diffusive character because this transition requires a structural change, and this also gives rise to the redistribution of atoms in the materials. And thank you very much.
Thank you very much.
It is not liquid, it is
Yes,
hard.
yes, I see it. But it's really interesting for me. What can be the smallest size of a sample which has still a property of memory shape? I'm asking that in connection with devices for information storage. The question was which can be the smallest size of a sample which still has the memory shape property. And I'm asking this because it is interesting whether this effect can be used for information storage. For instance, for
the shape memory effects is based on martensitic transformation crystallographically.
okay, but can we make a sample, for instance, from 1,000 of atoms, and will it still have this property or not?
Shape memory materials are used in many fields from here to the industry. And according to the purpose of the material, the user can select the size of the bir şey konuşmak.
So it is possible.
Do you have
Because I
any
am
questions?
physicist, I introduced the crystallographic and physical basis.
I see.
The users are most probably engineers and other people.
Thank you.
Thank you. I'd like to say conclusion phrases. Our first plenary lecture session is over, and organizers would like to apologize for this small photo break, which decreased in great amount